Welcome back to another explainer. Look at our planet. I mean, we call it Earth, but honestly, it should probably be called ocean. The global ocean is really our final terrestrial frontier. It's this vast, heavily pressurized abyss that has completely defied our understanding for centuries. And for the longest time, our exploration of the deep ocean, the benthic zone, relied entirely on just sheer brute force. We're talking massive, incredibly heavy tethered cables groaning under immense strain. We're talking wildly expensive, claustrophobic man-submersibles plunging into the pitch dark, facing unbelievable danger and cost just to get a tiny, fleeting glimpse of the deep before needing to immediately retreat. But there is a massive technological revolution happening right now beneath the waves. We are completely done using brute force to explore this alien world. Instead, we're finally outsmarting it. Okay, let's really dive into this. We have actually mapped the surfaces of Mars and the Moon with greater resolution than our own seafloor. Think about the sheer, staggering scale of that for a second. Right now, a massive 95% of the ocean's volume is completely obscured from human observation. 95%. That means almost the entire living space on our planet is a total mystery, hidden under this oppressive blanket of crushing pressure and absolute impenetrable darkness. It's an environment so unbelievably hostile that sending humans is nearly impossible, and sending traditional machines is incredibly inefficient.
So consider this explainer your mission briefing. First, we'll look at mastering the ocean's gravity. Then we'll face the terrifying reality of blind navigation and extreme pressure. Next, we'll decode the autonomous ocean brain of carbon sentinels. And finally, we'll glimpse the perpetual future of swarm networks. Let's get into it.
Chapter 1, Mastering the Ocean's Gravity and Outsmarting Physics with Buoyancy. We are completely moving away from the era of tethered submersibles and stepping right into the age of long-endurance autonomous underwater vehicles. Specifically, we're talking about buoyancy-driven gliders. This is the exact point where we stop fighting the ocean and start actually using its own physical laws to our advantage. The absolute heart of this machine is the buoyancy engine, and honestly, this completely blew my mind when I first learned about it. Imagine a person wearing a heavy scuba suit, right? But they're also wearing an inflatable vest. By adding air to the vest, their overall volume increases without adding any extra weight. That makes them positively buoyant, and so they rise to the surface. By letting the air out, they become dense and they sink. Well, the glider does exactly this, but it uses oil. It literally pumps oil from an internal reservoir out into an external bladder to ascend, and then mechanically retracts that oil back into its rigid hole to sink. And it performs this incredibly delicate dance with such astonishing precision that it can maintain a highly specific angled glide slope not just for a few hours, but for weeks or even months on end, all without ever needing to surface for a recharge. What's really interesting about this is how it completely flips traditional engineering on its head. Traditional submarines rely on massive propellers, which create a ton of energy-draining drag and introduce countless mechanical failure points that the ocean will inevitably exploit. But the buoyancy glider operates on a fundamentally more elegant law of physics. As the glider changes its volume to become heavier or lighter, it gains potential energy from gravity and buoyancy. Then, it takes that vertical potential energy and converts it directly into forward kinetic energy via lift. It relies entirely on a sustained vertical oscillation. So by simply sinking and rising over and over again, it transforms gravity and buoyancy into thousands of kilometers of forward travel. It's brilliant. And here is the actual physical secret to why that works so perfectly underwater. 800 times. Water's density is roughly 800 times that of the air we breathe. Just imagine trying to sprint through a waist-deep swimming pool. You feel that massive, heavy resistance pushing back against every single movement you make. Because the medium is so incredibly thick and heavy, you simply don't need a high-speed spinning motor to get traction. Even the slowest, most deliberate vertical movements generate massive, massive amounts of lift across the glider's fixed wings. Which brings us perfectly to hydrodynamic force. Picture this, you're in the pitch-black abyss, freezing water is rushing over these sleek carbon fiber wings as the vehicle slowly, silently falls through the water column. The fluid dynamics push against those wings exactly like a massive 747 banking through dense, turbulent storm clouds, but without a single sound. This hydrodynamic force allows the glider to seamlessly traverse incredibly strong deep ocean currents with virtually zero electrical output dedicated to propulsion. The ocean itself is literally doing all the heavy lifting. There's this quote from the research that I absolutely love, and it frames it perfectly. It says, "Consider this like a paper airplane thrown in a swimming pool. Because the water is so thick, even a very gentle, slow push keeps the paper airplane moving forward for a long time, without needing a motor to flap wings or spin a propeller. It just perfectly captures the sheer elegance and the almost unbelievable energy efficiency of how these machines glide through the deep." Moving on to Chapter 2, Blind Navigation and Extreme Pressure, Surviving the Hostile Deep.
Okay, so we figured out how to move efficiently, but we really need to talk about the environment we are moving through, because it is absolutely terrifying. The deep sea is one of the most hostile, unforgiving places on planet Earth. Surviving it requires engineering that honestly borders on the miraculous. Just let these challenges sink in for a second. You've got salt-induced corrosion aggressively eating away at any exposed metal. You've got extreme biofouling, microorganisms literally growing over and blinding your incredibly sensitive scientific equipment. And then there's the pressure. Down in the Hadal zone, the pressure can exceed 1,000 atmospheres. That is the equivalent of a 5-mile deep column of water pressing down on you from every single conceivable direction. Brittle, rigid structures, they would just shatter like glass under a hydraulic press down there. So, to survive this, engineers had to completely rethink their materials. These pressure hulls are often made of advanced synthetic foam, and they are designed to actually flex and compress rather than break under the immense, crushing weight of the ocean.
And this brilliantly illustrates how we actually gather data once we're down there. The foundational tool for taking measurements in that hostile dark is the CTD sensor. That stands for conductivity, temperature, and depth. Conductivity is basically a proxy for salinity. Think of it like testing the strength of a soup's flavor by how easily a spoon can pass through it. The more concentrated the salt and ingredients, the thicker the electrical resistance. This lets the glider precisely map out different invisible water masses. Imagine massive layers of the ocean sliding smoothly over each other without actually mixing. It's kind of like identifying the different floors of a skyscraper simply by stepping off the elevator and feeling a sudden drop in ambient temperature in each new room. But here's the crazy part. How does it even know where it is? Because GPS signals absolutely do not penetrate water. The second that glider dips below the surface, it is entirely on its own. It has to rely on a sequential, absolute lifeline of a process called dead reckoning. At minute 0, it takes its last known GPS fix from the satellite above. By minute 1 beneath the waves, it activates an internal compass and an inclinometer to measure its exact pitch. By minute 5, it crunches those numbers to calculate its current velocity vector. And by minute 10, it applies these incredibly complex mathematical corrections called Kalman filters to guess its path against invisible, shifting ocean currents. To really ground that complex Kalman filter math into reality, consider this analogy from the text. This is analogous to a person walking through a dark forest with their eyes closed, counting their steps and using a compass to estimate where they are relative to the last time they saw a landmark. Just imagine the sheer terror of navigating totally blind in a freezing void, getting pushed around by unseen winds, and being entirely dependent on mathematically counting your own footsteps in the pitch dark. That is exactly what this machine does every single day, completely cut off from the world above.
Chapter 3, Carbon Sentinels and Edge Intelligence, the Autonomous Ocean Brain.
So we've covered movement and survival, but the real magic happens when these machines start to evolve. They are actively transitioning from simple remote-controlled gliders into highly autonomous, intelligent sentinels capable of making their own decisions. A massive part of this evolution is achieving even greater endurance through phase-change materials, or PCMs. These are substances that automatically shift states, literally expanding and contracting, based purely on the ocean's temperature gradients. Imagine a tightly wound metal spring that naturally tightens in the freezing cold of the deep and seamlessly loosens in the warmer surface waters. By utilizing these materials, the glider essentially performs an infinite energy hack. It steals thermal energy from the ocean's natural stratification to physically power its own buoyancy cycles, completely without draining its onboard battery.
And what exactly are they doing with this endless endurance?
They're handling crucial real-world applications, like monitoring deep-sea carbon sequestration sites. As nations start injecting massive quantities of CO2 beneath the seafloor to fight climate change, we have to ensure it stays locked away forever. Because if millions of tons of trapped CO2 were to suddenly vent back into the water, the environmental damage would be absolutely catastrophic. So the gliders conduct continuous leak detection patrols. It's exactly like a security guard walking a beat in a dead quiet house in the middle of the night. But instead of using a flashlight, they're using a highly sensitive microphone to listen for the extremely faint hiss of a leaking pipe in the basement. They are literally listening for the exact acoustic signature of tiny gas bubbles escaping the deep sediment. So the crucial point here is that because water aggressively blocks radio waves, we obviously can't pilot these machines with a joystick. They are completely disconnected from human command for the vast majority of their mission. And that massive limitation actually forces the adoption of a monumental leap in robotics: edge intelligence. The onboard software has to be smart enough to make complex decisions instantly, right there on the edge. If the glider detects an anomalous methane plume on its sensors, it cannot afford to wait 6 hours to slowly ascend the surface and ask a human scientist what to do. The glider's own artificial brain decides to deviate from its pre-programmed path to investigate immediately. It is dynamically prioritizing its own flight safety and scientific curiosity on the fly. Chapter 4: Swarms and the Perpetual Future, the Final Evolutionary Leap. We are moving far beyond the individual drone now. We are transitioning into massive, coordinated, interconnected underwater networks. I really want you to think about this question for a second. The ocean's internal weather changes constantly. We're talking massive internal waves, rapidly shifting eddies, huge temperature spikes. How do you map the impossible when the terrain itself is moving faster than your machine? The answer is swarm-based oceanography. Instead of deploying one incredibly expensive, isolated glider, we deploy swarms of disposable microgliders. And because they can't use radio waves to synchronize with each other, they use what are called acoustic handshakes to talk underwater. Picture a vast mesh network acting like scouts scattered in a massive, totally foggy field. Imagine literal clicks, hums, and pings echoing through the freezing water over miles and miles. No single scout can see the whole picture, but by shouting localized acoustic information back and forth to their neighbors, they collaboratively build a massive, coherent, real-time map of transient ocean features that a single unit could never, ever hope to track on its own. And the physical hardware is getting just as smart as the software. We're talking absolute bleeding-edge biomimicry here, complete with morphing wings. As the research states, this is the difference between a bird that keeps its wings stiff while gliding and a falcon that pulls its wings in to dive faster or spreads them out to catch an updraft. By changing their wing geometry dynamically in real time, these gliders can literally sashay through highly turbulent ocean vortices. They are completely surrendering to the ocean's fluid dynamics rather than fighting them, adapting their physical shape second by second to maximize efficiency. It's wild. Let's see how this physical evolution builds into the data layer. Transmitting vast amounts of data via satellite costs an immense amount of battery power. So the hardware performs in situ analysis. It actually analyzes and compresses the raw data right there in the darkest depths of the ocean. It's like a librarian who, instead of mailing you an incredibly heavy 1,000-page book, just calls you up to read the title and a 2-sentence summary of the absolute best chapters. By compressing gigabytes of raw acoustic and visual data into highly valuable tiny metadata files, the glider saves massive amounts of battery and remains deployed in the field exponentially longer.
All of this, the gravity-defying buoyancy propulsion, the autonomous swarm logic, the in-situ data processing, it all leads us to the ultimate thesis of this technology, the perpetual mission. We are fundamentally shrinking the ocean. We're moving away from brief, incredibly expensive, expedition-based snapshots taken by passing research ships. Instead, we are moving toward a monumental transition, turning the entire global ocean into a persistent, constantly observable, multi-generational infrastructure. We are basically building an autonomous extension of the human nervous system and wiring it straight into the absolute darkest depths of the abyss.
Which leaves us with a truly staggering thought to end on today. Just think about what we've actually achieved here. If we can engineer autonomous machines to perpetually harvest energy from the darkest, most incredibly hostile abyss on our planet, what other impenetrable frontiers are out there just waiting for us to finally stop fighting physics and start writing it?